So here is the self-steering that I just made, and first of all is made with the 3D printed parts, and the other component is the shaft. There is a speargun tube, 30mm outside, 26 inside, in carbon, so very light and robust. And the vane itself is a pair of old carbon fins for spearfishing that they are old, so I just decided to change them, and being glued together front to front, two blades, and cut off the angle that go in the shoes and reused to build the reinforcement. So it came to be actually an excellent blade for strong wind. What happened, I just tested in the past days, with a strong wind around 30 knots, if you hold it, so you get overpowered, it just bend and flex the tip and let the wind escape. So it's actually very, very good at withstanding also gusts of wind, very strong. So all the parts are 3D printed, excluding the mount, of course, is stainless steel. And the wind vane, the trim tab itself, because this is a trim tab system mounted on a transom-mount rudder. So the trim tab itself is made in plywood with the shaft in stainless steel. It's a 10mm rod in stainless steel, and it is covered with just epoxy paint and polyurethane paint and anti-fouling. So now we'll go straight to how it's made. There is a few tools, so it's really made with super basic tools and a welding machine. So bands is a 40mm by 5 thickness stainless steel plates, and they're bent and shaped and cut, so see what fit your rudder, but to make the I don't know how they're called in English, the supports for the rudder. And then I don't have the picture, but basically the shaft of the trim tab is a rod, is around 1.2 meter long, and I weld on top of it some pieces of 40mm by 5 thickness stainless steel plate to create the reinforcement inside, so you get a grip. And the two layers is 12mm plywood, is glued on each side. It's 16mm plywood, yeah, and it's glued with epoxy glue. Of course I open the channels and make the holes for the plates of the shaft. So it's glued together, and I've been very, very careful not to leave any bubbles inside. So there was plenty of epoxy filler that has been made, just epoxy and microfiber and colloidal silica. Until it just squeezes, until it's coming out all the excess. It's a bit of a waste of epoxy, but it's important not to have air bubbles inside, where the water, by capillarity along the shaft, because the shaft is stainless steel, will one day create capillarity, and the water will go inside, and you never know what happened. So after it's hardened and it's been cleaned up, then I just went on a website, one of the many online, and printed on a piece of paper a profile, NACA profile that seemed, I have no idea which one is actually the best, but I took one that looked like good enough and plotted it on a piece of paper, cut it out, and then with a marker I just roughly mark the outline using the paper as a template, of course, on the head and the two sides of the plywood, and then with an angle grinder with sandpaper, like P80 or I don't remember, P60, something very rough. I just shaped the plywood without taking any care about being precise, because I really don't care on this stage. Also because you can't actually be so precise, so it's a pain in the butt, and a better way to make a proper profile. So it has been just roughly shaped. Of course, the lines in the plywood help a lot to make it right. But what I'm saying here is better to remove some material more than leave too much wood and bumps. You'll see later why. So shape both sides, try to keep it symmetric, because the trick here is not to get the perfect profile. The trick is to have it symmetric on both sides, because what you don't want to have the water to flow in a different speed in one side or the other of the trim tab, and then deviate the trim tab itself, changing the speed of the boat. So we really want to have it symmetric. To do that, once as the plywood has been roughly shaped and leaving actually some holes, I cut on a piece of thin plywood the profile that was designed before, like as a sort of a form. Then I put epoxy filler, lightweight epoxy filler, abundant, on top of the wood, and using the shape that I cut on the thin plywood, just start in one side, pull it until the other side in one single motion. Very nice. Remember that the better is enemy of good. So if you try to go twice, you will make a mess. So put your filler on top, start in one side, pull it in one single motion. Is good enough. Okay, stop. If it's blobby or there are things that pull out, just put back the filler and start again. There's nothing worse than go many times on top of the same work with a spatula or a shape like this, because then it's messing up everything. So you make one pull, let it, okay, when it's nice and good enough, then you let it harden. Then you turn it and you do it on the other side. Remember, of course, to clean your spatula, your shape there. And then the blade is, the trim tab is actually done. At this point is necessary to have some protection, so some good sandpaper, shape the corner round, and then I put 3 or 4 layers, so I don't remember, of epoxy resin on top as a protection. And polyurethane paint, 2 component, and then epoxy. Antifouling. By the way, remember, between the different layers of epoxy and polyurethane, you need to, don't wait too long. Have a look at the data sheet when you buy these materials, and there's always an open time indicated there, depending on the temperature. That is when the time to which the surface of the epoxy or polyurethane is still open to receive the next layer. If you wait too long, like give a hand of epoxy now and outside is warm, then you do the work again in 2 days, you will have to mechanically treat it, so basically sandpaper, because otherwise the next layer will not have a good adhesion, and the same go with the polyurethane. So then when the trim tab has been done, I did something that was considered impossible by the shipyard that built the boat. That I called them, and I was a bit surprised. They say, no, it's impossible to take the rudder outside of the boat, off the water, when the boat is still in the water. Okay, it took 20 minutes, free diving, not even with the bottles. 20 minutes to remove the supports and pull it up, and around a couple of hours actually to put it back. So the damn bolts, there are 2 supports with 4 bolts each, and everything has to be super aligned. So to get in and do it while free diving is a bit pain in the butt, and especially when the water is freaking cold, like here in Denmark. And it was actually pretty cold in the harbour. So, and by the way, a couple of hours and job has been done, and the rudder is back in place. Then it came the part with the head. Now the head, I built this stainless steel support on the back that work as a support exactly for the main shaft of the vane, and also as a protection, because especially on the back they made a sort of pipe and thing can be seen in some picture, in the last pictures, because in the harbors here sometimes are very crowded, and there are many German sailors that normally are very, very good sailors, but there is really sometimes a horde of beginners, and everybody's coming here, and then in crowded harbors I've got so many times my self-steering damaged one way or the other by these guys. They come very, very close, and they have big boats and they have no freaking idea how to use them or even how to moor them, so the wind just move them and can start to hit my boat. The classic. Now I've made a stainless steel protection, so good luck to them. Anyway, so when the design has been done, the 3D part, I print them on a 3D printer. Is a homemade 3D printer, so nothing really super fancy, and is I use a PCTG filament on 240 degrees and 0.3 millimeter layers. So is I don't care if it's pretty or not. Actually, it's not pretty. It's full of say the surface is not super nice, but who cares? The important is the layers have the best adhesion, and actually they have. It seems to be very, very strong, and I tested it at work to do other constructions, and actually it does very well. The material is absolutely much more robust and has a very, very good layer adhesion, and also is totally waterproof, so it doesn't absorb humidity, and it withstands ultraviolet light quite well. Now I haven't checked that because I just made it, so let's see after the summer. If I start to see some surface change, I will just paint them, and that's it. Once all the components, and by the way, if you want to have the drawings and 3D model is a Fusion 360 model, just send me a message, and I can see if I can send it to you, so you can actually adapt it to your boat. But once everything has been put together, I put the cables, and the system work with I had a couple of meters of PTFE piping for tubing for the 3D printer. Was an old project, and then I used that as a sheet. And then it was like 2.5 meters max that I used, and then I used this the cable, stainless steel cable for the gear shift of mountain bikes. So it's also some very low friction coating, and it actually does very well. So put in the head, run it down, and the control actually. It has to be positively dampened if you want to have the rudder to go back in its original position in case you get a wave. And the point of damping is actually moved by moving far apart or closer together the two points where the PTFE piping is fixed on the support. Now this was the first trial that I did. It worked beautifully, so I'm not going to touch it again. So they are basically 40 centimeters apart, so 20 right, 20 left. And for the geometry that I have on the boat is working beautifully. Now how the link is made with the trim tab. The main thing here was that the trim tab, normally there are huge pain in the butt in when you go reverse in the harbors. They tend to really be in the way, and if you don't lock them in the middle perfectly, either they try to steer themselves, the rudder instead of you, or they go traverse and then they crack, and for sure you're going to break something. I've got many self-steering before with other boats, even commercially made one. And if you forget the blade in the water and it traverse, it break. It could just crack. So that was my main concern. And also here in Scandinavia, they have this nasty habit of having these sticks in the middle of the harbor. So with these poles everywhere, which are totally useless. But I mean, they have these. So these poles, and when you try to get out of the poles, especially a short boat like the one I have, it's only 27 feet. When there is a lot of wind, you really need to watch like an eagle where you go with the back, because when you have the self-steering on the back and going to hit it on the pole is not really nice. So that also damage can happen. So the main thing was that the trim tab should give no resistance whatsoever when the boat maneuvers in the harbor in reverse, even at full speed. And the only way I found was to allow the trim tab to rotate 360 degrees freely. Now, to do that, the shaft coming out of the trim tab is a 10 millimeter full 10 millimeter stainless steel. Then I've taken a piece of tube. This is a 25 millimeter external diameter stainless steel tube. And as you can see in the picture, put a small collar with a little piece of plate welded on. It's a 5 millimeter plate, little piece welded on, and then there is a channel cut in the tube, and I put a washer as a bottom, 10 millimeter washer, so it doesn't have a gain on the much gain on the shaft. So what happened that this tube, when it's lifted up couple of centimeters, it is completely disengaged by the main shaft of the trim tab. When the tube is lowered down, the piece of metal in the collar rotate and find the slot in the tube, just slid in, and the two are locked together. So, and it worked perfectly, because now what I can do, I just of course, the tube is the part where there is a big pulley. The big pulley is attached to this tube, and is what is the link actually with the wind vane. It happened with the cables. So what happened when I lift up the pulley and the tube a couple of centimeters, it just disengage the trim tab and is free to rotate. When I'm in sailing and I want to engage the self-steering, I just release it, and it's just a small rope that I put with a cam lock. So basically just release it, it falls down by gravity by itself, doesn't need any help, and is slit in the main shaft. They get locked together, and immediately the wind vane start to act and change the trim tab orientation. So the system works beautifully. And here there is a small video where I've done a test today, and 10 knots of wind, 10, 12 knots. So going with the wind on the back, the wind vane was the vane was way too small. Also because there is around 3 knots of current here on the strait of the horizon. So between the speed of going with the wind on the back and the current, there was like maybe 3 knots of apparent wind. So the vane was absolutely not able to steer anything. Instead, going on attack, it was just beautiful, and it's absolutely precise. And in the video here, I will make a small tack. I've done several tacks, and it's just super easy, because just rotate the wind vane in the new direction, and you don't have to care about the tiller, about the main and anything. So I just rotate, lock it again, and then take care of the sheets of the Genoa, and that's it, and it's done. So it's just working really nice. Now next step will be to test it with some good strong wind, which for luck here is actually the opposite, is to find these calm days to test for the first test of the self-steering. That is difficult to find in this season. But as soon as the wind pump up again, like 15, 20, 25 knots, I will go out again and see how it performs with a bit more wind. And then we try on a storm one day when it comes. Why to test self-steering in low wind? Well, because if something goes wrong, it's much more difficult to destroy everything. the forces in game are much lower, and consider it's not going to be proportional, it's going to be exponential. So between 10 knots and 20 knots there's a huge difference on the gear. So if something goes wrong, you can always fix the problem, or just disengage everything and nothing break. If there is a lot of wind and something goes wrong, you have no time to react. Just crack down everything. And unfortunately, I've done that before. So hard lesson learned. So yes, when we have some more information, it will come up. But basically, this self-steering on this boat, which is a long keel boat, it keeps absolutely straight. I know that there is a S-shaped wake behind the boat, but I really can't see that. It was going so beautifully and so straight. It looked like there was a tiller pilot engaged. So it's absolutely fantastic. So I'm really satisfied of this. Also, we'll have to build a much larger wind vane, the vane for low wind and when we run on spinnaker, because the apparent wind would probably be like 5 to 6 knots. So I've seen that this was moving, but had not enough force to push the trim tab in that situation. So it need to be larger and longer, especially. So this is 419 grams with a center of mass that is 24 centimeters from the base of the vane. So I need to make a larger vane that has exactly the same characteristics. So the same center of mass at 24 centimeters from the base and 419 grams in total. This way I can just replace the two vanes without changing the position of the lead ballast on the head. And this is very important, otherwise you need to recalibrate everything every time. It's a pain in the butt. Okay guys, see you at the next video when things will be tested more thoroughly. Ciao.